Welcome back, everybody. I'm pleased to present the next speaker, Inoue, and she is going to speak on cluster realization of Weyl groups and applications to representation theory.
Thank you very much. It's my great pleasure to give a talk in this big, beautiful conference. So it's my first time to attend FPSAC, and I'm very surprised to have so many people here from all over the world. So I shall explain my affiliation first. So Chiba Prefecture is next to Tokyo. So if you have been to Japan and fly to Narita Airport, so this is in Chiba Prefecture. So yeah. Then my talk is based on a collaboration in these 7 or 8 years with these people. Oh, sorry. With these people. So, in my talk, I use cluster algebra. And I'm afraid some of you are not very familiar with this one. So I'd like to explain a very basic notion first. So cluster algebra was introduced by Fermi and Derbinsky around 2000. It is a commutative algebra defined in the following way. So we first fix a finite set. For example, it's a set of integers from 1 to n, for example. And we prepare a seed. This is a triple of a skew-symmetrizable integral matrix, epsilon. And it means that there exists some diagonal integral matrix such that epsilon d is skew-symmetric. And moreover, we have two tuples of variables. One is called cluster variables, or A variables in my talk. And second one is called coefficients, or X variables. So in the original definition of Fermi and Derbinsky, they write small x and small y for these variables. But for some reason, to follow the definition of Fock and Gonchar in geometry, so I prefer to use A and X for today's my talk. Then, for such a triple called a seed, we have some procedure to get new seed from the given one. So for k, if it is the element in this I, we define mutation mu k. And we get the new seed, new triple of like this. And by the definition, we get, by applying many times of mutations, we get many seeds. And it is easy to know that each mutation, mu k is involutive. So we have n3 in this way. And the definition of cluster algebra is that it is defined as the algebra generated by all A variables in all seeds. So this is a definition. So the fundamental problem in cluster algebra is that if the number of A variables or seed is finite or not, so it depends on this skew-symmetrizable matrix very much. So this is a very rough definition of cluster algebra. And more precisely, the mutation is given by this formula. So please don't try to memorize this one. It is just a relation. So roughly speaking, so skew-symmetrizable matrix is changed in this way. And we again get a new integral skew-symmetrizable matrix. And the matrix D, the symmetrizer, is the same. And for X and A variables, we get some rational transformation depending on the matrix epsilon. Then I'd like to make that if epsilon ij is 0, then the corresponding mutations are commuting. And moreover, we started with a pair of skew-symmetrizable matrix epsilon and D, but we also use the description of this pair by using weighted quiver. So this is a pair of skew-symmetric matrix sigma given in this form, and the same D. So we assume that the weight of ith vertex is di. And so for this Q-symmetric matrix, we can draw a weighted quiver where sigma ij is the number of arrows from the ith to jth vertex minus the number of opposite arrows. So because we don't have one loop and two circles in the quiver, so this correspondence is 1-to-1. So this is a very rough introduction of cluster things. Then this is an example. So this is already a quiver, and we assume all weight of the vertices are 1 in this case. This is two variables. And let's mutate this quiver at vertex 1 here, and we get this quiver and these variables. And the rule is roughly, if we mutate at vertex 1, we first reverse all arrows related to 1, like this. And if there is a pair such that one is coming to vertex 1 and another is outgoing from 1, then we add this arrow to make oriented triangle like this. So we do this way for all such pairs. And finally, we add the remaining arrows. This is a rough description of the mutation. So we apply next the mutation at vertex 2. In the same way, we get this one. And in this case, these and these arrows are, disappeared because of because we have two cycles here and here after mutation, and we erase that. So A and X variables are transformed in some complex way like this. Then, by using such a mutation, I'm interested in to find some interesting rational transformation or rational map by using this cluster things. So I forgot to say that if we assume the weight of vertex 1 and 4 is 2, for example, and the mutation becomes a little bit different, like this. We have a square or something like this. So this small change occurs. I'm sorry to forget this one. And so my idea to study something, for example, I'm interested in integral systems and related various topics in representation theory or combinatorics or geometry or so on. So basic idea is very naive. So if we have a quiver and some sequence of mutations, for example, the length p mutation, which preserves the quiver itself, then we can iterate on this sequence of mutation for many times. And finally, we get a rational map on the rational functional field generated by A or X variables. So if we have some interesting rational map by using mutation, then we can apply many techniques in cluster algebra. So sometimes the proof of periodicity is drastically simplified due to cluster structure. So we are interested in to find such a rational map, useful one. Then this is an overview of my talk. So today I will introduce a cluster realization of Weyl group by using two family of quivers, Q or Q prime. Then actually the first one has various applications in representation theory or Q-Pandover equation. It is a kind of discrete integral system, and higher Teichner theory initiated by Fock and Gonchorf, or a positive representation of finite quantum group, or so on. There are many, many things. And on the other hand, for second family, Q prime, this is a new one. And for this one, we have an interesting application in class Q character of affine quantum group. So for the first time, I plan to talk both of this, but I knew a week ago, I was noticed that the time is 50 minutes. So today, I prefer to talk about this first, and next I go to this topic. Okay. Then let me explain the Weyl group. So I quickly recall the notion in Lie algebras. Maybe already all of you know. So let G a finite dimensional simple Lie algebra of rank L. So S is the rank set from integers from 1 to L. And I write C for the Cartan matrix. And here alpha I is the simple root. And I introduce number di. So this is a half of the inner product of alpha I. And d is a minimum of them, and d prime is a maximum of them. Then this is a very famous classification of finite dimensional simple Lie algebras. So when the Dynkin diagrams are simply laced like ADE, then we have only one for di, but the ranks of roots are different like B, C, F, G. We have some different numbers for d and d prime. Then I introduce quivers, two families of quivers. The first one is Q. So first we prepare a Dynkin quiver for G, and please recall the numbering of Dynkin diagram like this. And by using this numbering, if we have an edge between i's and j's vertices in the Dynkin quiver, and if I is smaller than j, then we draw an arrow from j to I, and we prepare m copies of such Dynkin quiver. Then we align them on the cylinder. And so the vertex set of the quiver QMG is given by VIN. I is in the rank set, and N is M periodic lattice. Then we assume that the weight of VIN is di over d. So it depends on the length of the root. Yes, the length of the simple root. So this is an example of G is A4. Here, all vertices has weight 1. Then we prepare these Dynkin quivers. In this case, we have M is 4. And so this red rectangle denotes the fundamental domain on the cylinder. Then we add these arrows. So we have this vertical line and diagonal line. And please note that if we fix I, the element in the rank set, we have a vertical line for each I. So the next example is the case that G is C4. In this case, we have weight 1 for I is 1 to 3, and the fourth simple root is longer, excuse me. So we have weight 2 for the last line. Then in both cases, we have, so for each I in the rank set, we have directed closed path. So this is a vertical line like this. This is the first family of quiver.
Sorry, did you have a rule for the diagonal and vertical edge? How did you?
Yes, the question was, so do I have the rule to the direction of arrows in the quiver? So actually, the rule is very simple. So we have a vertical line from top to down about the vertices of the same rank. And for this diagonal line, the rule is that we have oriented small triangles. Yeah, actually, we can change the direction of Dynkin quiver, but we have to follow the other rules. Yeah. Then this is the first family of the quiver. And second one is a little bit complicated. And the Q prime is same as the previous one when G is simply laced. But if it is not simply laced, then we have a different quiver from the previous one. So in this case, we have different D and D prime. So by using these two numbers, we define this. Maybe it is a half lattice with some periodicity. And we assume that all weight of the vertices is 1 in this case. So let's see an example of B4. So in this case, we have this quiver. So we have this D, 1, 1, 1 and half. And because of this half, and the line for the fourth link has half unit size. On the other hand, for the first link, V1, we have 2 oriented closed paths like this, and 2, 3 is the same. So consequently, we have PI1, 2 for I is 1 to 3, and P41, it is the only closed path for the rank 4, and so on. So in general, we have, depending on I, we may have oriented closed circle for a given I more than 1 in this case. And so next example is the case gauge C4. It is really a dual to B4 case. In this case, we have D is 1, 1, 1, 2. And for the last rank, we have 2 oriented closed paths like this. And now the unit size of this lattice is 2. And so for the other one, 1, 2, 3, we have 2 closed paths for each. Only 1 closed path for each. And so only the fourth one has 2 oriented closed paths. So today I omit the explain of a F and G case, but you can imagine those cases by using this duality of B and C. So to realize the Weyl group, we use this interesting mutation sequence introduced by Bücher in 2014. So for a directed closed path P like this, it has small p lengths. Bücher introduced a sequence of mutation and permutation like this. So we start with vertex 1 like this, mu1. And we apply mu1, mu2, and we come to mu p. Then we interchange the last 2 vertices. Then we skip these last 2 ones, and we restart with p minus 1. And by using the opposite order, we come back to mu1. This is a mutation sequence. And we also define a polynomial in x variables on this quiver. Then, interesting phenomena is as follows. So this mutation sequence preserves the quiver P. But A and X variables are changed non-trivially like this. Then, actually, this mutation sequence is very interesting from the viewpoint of cluster, I think. And so we use this mutation sequence to define a Weyl group realization. Then please recall that there are many oriented closed paths in the quivers Q and Q prime. So we define this kind of mutation sequence for each of them. Then we get the following result. So first, in the first family of the quiver, Q are related to the Dinkin quiver. We have R, P associated to a closed path Pi, started with vertex on Pi, say VIN. And each of them preserves the entire quiver, not only closed path, but also the entire one. And actually, we can show that the action on the seed doesn't depend on the starting vertex on the circle. So for simplicity, we write Ri for this one. So it doesn't depend on n. The second, actually, we can show that this Ri I runs from 1 to L in the rank set, they generate the Weyl group action on the rational functional field. Because it preserves the entire quiver, we safely define the rational map on this rational functional field generated by x or a variables. Namely, it satisfies the Coxeter relation. So this MJ is determined by the Cartan matrix in this way. And when the Cij times Cji is 1, for example, then this is nothing but the braid relation or so on. And so it is very nice realization. And for the second family of the quiver, Q prime, we have a very similar phenomena, namely mutation sequence for each oriented cross path preserves the entire quiver, and the action doesn't depend on the starting vertex on the path. And moreover, in this case, if we fix I, the rank, then we may have more than one oriented cross path P. So we can show that the corresponding R are commuting. So we define new Ri as a composition of such a commuting R with the same level I. Then we can show that these Ri generate the Weyl group action on the rational functional field in the same sense as before. So we have two realization of Weyl group in this way. So it is very simple and very, how to say, elementary in some sense. Then let's see what's the difference between them. So this is a very short example of the case gate is A3 or C3. So in C3 case, a different part from A3 is written in blue color here. For example, D is, in A3 case, we have 1, 1, 1, but in C3 case, we have 1, 1, 2, and so this is a Cartan matrix. Then the action of R2 and R3 on the first family of quiver, Q, is, for example, given by this formula. And the difference is only this power. So it is a very small difference. And on the other hand, in the case of the second family of quiver, Q prime, let's compare this with the case of the previous case of C3 case. So the difference is denoted by underlines here and there. So in the first case, we have power 2, but it doesn't have such one. But total number in numerator, total number of x variables in the numerator is the same or so on. And on the other hand, because the unit size of the oriented paths are different, so it appears here and there, and so. This is a very, very small difference, but it is essential for the different realization. Then, I'd like to remark that in both cases, the Weyl group action on the x variables is analog of the Weyl group action on the root system. So you can see that, for example, in the case of the first family of the quiver, the induced action on this big X, which is the multiplication of all x variables on the oriented path, is simplified as this. So all polynomials f in numerator and denominator are cancelled on a circle, and we get only this part. So this is nothing but the multiplicative version of the action of the Weyl group on the simple root like this. So we can say that these x variables are the loop analog of the simple root. Then the situation is similar for the second family of quiver, Q prime. So this was the introduction for the Weyl group action. And I'd like to apply this to representation theory from now. So there is a big background of Q character for the affine quantum group UQ gay hat, but today I take only a small part we need today. So Q character and screening operators are introduced by Frankel and Reshtekin in 90s. And so here, UQ gay hat is an affine quantum group. So gay hat is a non-twisted affine real algebra for gay. And we fix a non-zero complex number Q, then assume for a while it is not a root of unity. Then they define the Q character map, chi Q, from the Grothendieck ring of the category of finite dimensional representation of this affine quantum group to Roland polynomial ring generated by commuting variables YIA. And here I is in the rank set, then A is non-zero complex number. So this map is called Q character. So roughly speaking, it takes a trace of some representation. Then they are interested in the image of this character map, and they fix the image in this way. It is implicit way somehow. So because if we fix I in the rank set, we have this subring of this one generated by these variables. It is complicated one, but important is that this J is different from this fixed I, and the I's part is only this one. Then here, A is given by this formula. This is a kind of Roland monomial in Y. Then the image of the character is the intersection of this complicated subring of Y. So it is very not easy to understand this ring, but they give some interesting interpretation. So before that, I'd like to remark that this Y is related to the loop analog of fundamental weight, and A is nothing but the loop analog of simple root. So they are related by this formula. Then another interpretation of the image of Q characters came from the study of Q deformation of W algebra, which is W algebra is a higher generalization of Virasoro algebra, appearing in variously in mathematical physics too. So they try to deform this W algebra for this quantum affine quantum group. Sorry. Then, for that purpose, they need to define a kind of operator called screening operator, and it is a very curious operator. So it sends this ring Y to some different ring with this decoration. So this is basically it is a linear map. Then it is called a screening operator. So this S isn't related to variables Y directly, but through A, they are related. So they consider some quotient space of this one by introducing this relation. So it's a complicated one. But the next theorem is very beautiful. So they proved that so first, Frankel and Reshtekin conjectured this theorem, and soon later, Frankel and Muhin proved this theorem. So the intersection of the kernel of this curious screening operator is nothing but the image of this character. So more precisely, a kernel of each Si is nothing but this subring of Y. So the character map and this action of the screening operator, they are very different, but they have some common structure here. Then I'd like to show a simpler example here. So when gay is A2, the character for representation associated to fundamental weight W1 is given by this formula. So then we can rewrite this expression in two ways by using the relation, this one, in two ways, like this or this. And you can see that in the first expression, it is really in the kernel of S1, because this part is nothing but this one. If you fix I to be 1, then we have 2 and 1. So this is nothing but this expression. This belongs to this ring. So it is in kernel of S1. On the other hand, with the second expression, we see that this is in the kernel of S2. So this belongs to this part, and this belongs to this part. So it's really in the intersection of S1 and S2. So in this way, we see some idea of them. And the question is that as follows. So the character of D group K of G, so without deformation parameter Q, we have a usual character map from the Grothendieck ring of the finite dimensional representation of G to Laurent polynomial ring generated by Y. This is commuting variables again without A. So it only has a level of rank. Then on this ring, we have natural Weyl group action. We can imagine easily by the action of the Weyl group on the fundamental weight, like this. And here, A is again the multiplicative version of the simple root given by this formula. So the question is that, so what is the Q analog of this Weyl group action? So it is not known. It was not known. And moreover, if there is some analog, then what is the relation with screening operators? So we naturally guess that if such a Weyl group action exists, it should be related to screening operator. Then this problem is solved recently. So first I introduce my result on the case that Q is root of unity. So in this case, we safely apply the Weyl group construction in the first part in this case. But unfortunately, there is no definition of screening operators if Q is root of unity. So we don't have the second problem. But for generic Q, Frankel and Hernandez solved this problem finally in the last year. So in the remaining part, I'd like to explain this result. So for that purpose, I move to the variables on the lattice by stratifying this non-zero complex number A. So we consider this rational functional field now, because Weyl group action is a rational map. So we prefer to use this field, and we fix one non-zero element A and define this subfield of this one. So we consider A times Q2 something and only. So N is in the lattice. This D is what I defined in the interaction Lie algebra. So here delta, it depends on only I, so it is not important for today's talk. It is too detailed, so I omit the definition. But the point is that we only consider Y variables with A Q2 to N plus something. So it is satisfactory to think this stratified version. Then we change just the notation variables from this to YIN. It is easier to see. So this map phi A is just for the change of the notation. Then we see that the stratified image of the character map is written as this now. So it is an intersection of this ring. Generator is this one, and J is different from I, and so on. Then this X is the image of phi A of A inverse, so like this. And this is, so A was Laurent monomial in this Y, and now X is Laurent monomial in this small y, and so on. Then, so we consider Q character at the root of unity now, and we assume this Q is epsilon. It's different from the skew symmetrizable matrix in the definition of cluster algebra. I'm sorry for this confusion, but this is just a complex number. E to 2D prime M is 1. We take this root of unity from now. And in the case that Q is root of unity, we have the following fact. First one was proved by Frankel and Muhin. So they introduced the Q character map in the case Q is root of unity safely. And their claim is that the Q character map now is the same as the case of generic Q, but we just restrict the class of representation a little bit. Then its image is again have the same form like this. So it's the intersection of this subring of this one, and the generator are the same. But we just add this periodicity corresponding to this condition. That's all. So the Q character is well defined also for the root of unity case in this way. And moreover, these variables, small yin, can be regarded as variables on the second family of quiver, Q prime. So roughly speaking, this lattice is the same as the vertex set of this one. And moreover, this X is nothing but the X variables for Q prime. So more precisely, the Poisson structure of X is naturally introduced by the structure of this quiver, and it is the same as the expected one obtained from the Q character structure. So they are really the same one. Then actually, this quiver, Q prime, was first introduced when M is infinite case, half infinite or infinite case by Hernandez and Leclerc in 2016 in the different context. They are interested in the cluster structure of the Q character, and they introduced the very essentially the same quiver. But now we want to use this quiver more naive way. Then, so we already have a Weyl group action on the rational functional field generated by X variables, and we want to extend this action to that of small y variables. So for this purpose, we define this rational map on this rational functional field. So by using this one. So because X variables, this one, is written in terms y as Laurent monomial, it is safely defined as a rational map on this field. Then we can show that this small Ri generates the Weyl group action on this extended field. So more precisely, we have defined a Weyl group action on the cluster X variables in the first part, and now we define this part. and via this embedding map of the fields, this diagram is commuting. And so we safely can define the Weyl group action on this field. Then moreover, interestingly, the image of the Q character is included in the invariant subfield of this Weyl group action. So especially, please recall that the image of Q character is an intersection of these Zi given by this formula, and each Zi is included in the invariant subfield of Ri. It reminds us of the situation of screening operator very much. Then, moreover, in this case, we don't have a screening operator, unfortunately. We cannot go to screening operator side, but we want to fix this field more precisely. So, namely, we want to compare this and this. And for that purpose, we define the quotient of this Z, and we generalize the coefficient from Z to C to simplify the situation. Then we consider this rational functional field generated by generator of Zi, like this. And we compare this invariant field and this field, subfield. Then result is this one. So when the root is shorter, namely di over d is 1, then they are the same. But the root is longer, namely di over d can be 2 or 3. We have to add a finite number of elements to make this equality. So this delta is a very interesting factor. This is the Laurent binomial in small y variables given by this formula. This is a global variables. And so it itself doesn't belong to Zi, but by making a square, it belongs to Zi. So by adding such things, we get this equality. So this measures the difference between these two. I'm interested in what is this from the viewpoint of representation theory, but for now, I have no idea. So this is the result for the root of unity case. And finally, I'd like briefly introduce the result by Frankel and Hernandez. So the idea could be the following. So we consider the Weyl group action on the small y variables, and now the characteristic one is this polynomial f. So it was a polynomial in x variables on a closed oriented path. So now we can assume that it is not a circle anymore. So we have to introduce this kind of thing. So formal series in x variables on something. But in this case, if we use a quiver naively, the number of the length of the circle is infinite, so it is useless. So we have to be abstract. So the problem is that, so what we can define this in this as a formal power series, it's okay, but the problem is that what is an appropriate space where this action is well defined. And so Frankel and Hernandez solved this problem by using a very nice space, pi. So this is a certain completion of this Laurent polynomial ring as a direct sum of rings on formal power series. So the definition of this space is very complicated, but the idea is it might be too detailed, but the idea came from the category O. This is a category of representation of quantum, affine quantum group, including infinite dimensional one. So this is a good class of infinite dimensional representation of the affine quantum group. So it also needs some completion, and this completion is the same as this one. And by the way, so anyhow, they can safely define a good space to apply this operation. And to get the well-defined one, they have to generalize this naive action in some way. But finally, they show that it generates the Weyl group action on this good space. Then, moreover, please recall the existence of a screening operator. So in the lattice case, it is written as this. So for yj, we multiply some s if I and j are the same, and so on. So they solve the second question in the following way. So they extend this f hat, this formal one, by using infinitesimal parameter h. Then in the limit h goes to 0, we have this expansion in h of the action of r hat, naively. So here, this is a screening operator. And so by using this expansion, this is written by using f hat in this way. This f hat, sorry, with h. We can rewrite this one. So it is a very good result because by using this relation, we can see that the kernel of Si, the relation of kernel of Si and the invariant subfield of R, we can see this correspondence. And in particular, we get that the image of the Q character, Y, is nothing but the invariant subring of Weyl group action by using this relation. So now they gave a very nice answer to this long-standing problem. So this first equality was proved by Frank and Muhin in 2001. And in the last year, this equality was proved. And now we can know the relation with screening operator and Weyl group action completely. So I think this kind of construction can be applied to get some interesting integral systems also. So I'm interested in that aspect for now. So this is the end of my talk. I'm sorry that I didn't talk anything about this, but if I have another chance, I will try. So thank you very much for attention.
Thank you so much. Are there any questions?
Yeah.
I'm just wondering if there was a relation between the first part of your talk and zamological periodicity.
Zamological period in the first part, you mean?
Can you repeat the question?
Yes. His question was, so is there any relation with zamological periodicity? Yes. Actually, in the first part, I introduced the Weyl group action. And so if you, there is some periodicity. So more precisely, if you take the longest element in the Weyl group, and if you apply the corresponding sequence of R, the generator of Weyl group, then you safely you can prove that it is a maximal green sequence. So it's a terminology in cluster algebra. So by using this, you can get some periodicity. Thank you.
I was wondering also whether there was any relationship with the work of Iwaki and Nakanishi on exact WKB analysis in cluster algebras, because they also kind of construct these rational maps on these of similar-looking fields using sequences of mutations. So yeah.
Yes, the question was, is there any relation with this paper by Iwaki and Nakanishi on the WKB analysis by applying cluster structure. I have no idea about that. I'm sorry. So I think it is a different story. The cluster algebra is common, but the direction is a little bit different, I guess.
Other questions?
Hi, could you say a little bit more about the screening operator?
Yes?
I guess fully understand that, or like more so its purpose or something like that.
Yes. So his question is, can I explain more about screening operator? So to define, where is it? Oh, sorry, this one. So the W algebra was originally defined as the kernel of screening operator in the original setting. So it might be not answer your question, but so the Virasoro or W algebra, if you take some specific definition, and we essentially have a screening operator. And so in this case, we want to get its Q deformation to define a Q deformation of W algebra. This was the motivation of Frankel and Reshtikin to introduce this curious linear map. Yeah, I'm not familiar with the physical side of screening operator. Sorry on that.
Anyone else?
As I know, there is a T analog of Q character introduced by Aragonese.
Yeah.
Do you consider a T analog your bicorrection?
T analog, you mean? The question is if there is a T analog, more deformation of this one.
Yes,
Is it your question?
Then there is a T analog of Q characters.
Yeah.
T analog of screening operators.
Is there T analog of screening operators?
Yes, the same question. Aragonese introduced it and 2004.
I see. I didn't know that in detail. So maybe it might be possible, but so his question was about T analog of Q character. It is, so here, Q deformation is on the commuting ring, like Y, generated by Y, but T analog, for T analog, we have this Y is non-commuting. Is it right? So I have no idea, but there might be something more deformation. But I'm not sure if cluster algebra works well. I have no idea about that. But it might be interesting to study T analog, more deformation of this structure.
Other questions? If not, let's thank the speaker.